Alright, so here we go. We are going to be looking at Chapter 5, which is Circular Motion, the Planets, and the Gravity. In this particular video, we are going to be focusing on circular motion, specifically uniform circular motion. So when we look at uniform circular motion, one of the first things we think of is an object on a string. So if we have an object on a string and we are spinning it in a circle, and that string breaks at a point, it is important to realize that that object is going to go straight off at that point with a velocity that is tangent to that circular path at that point. This is Newton's first law of motion in action, that the object in motion will continue in motion unless there is an external force acting on it. Now, eventually gravity will act on it and will therefore pull it down, but until that happens, what you have is the object moving immediately in a straight line path tangent to the circle. When we look at centripetal acceleration, which is the acceleration of an object moving in a circular path, we have to recognize that that is the rate of change of velocity of the object associated due to the change in direction. Now, since we are focusing on uniform circular motion, that means that the magnitude of the velocity is constant. So it's like you have the cruise control set on your car. So the magnitude is constant, the only thing that is changing is the direction. So what you find is if you look at the change in velocity, the change in velocity is a vector that is directed towards the center of the circle. It is perpendicular to the path at that point. Therefore, what you find is that the centripetal acceleration is always perpendicular to the velocity vector. It is always directed towards the center of the circle, or radially inward. So, how large is centripetal acceleration? Well, no doubt you've probably traveled on-ramps and off-ramps, and no doubt you have experienced that if you're going faster on an on-ramp or an off-ramp, that you will feel a greater acceleration. No doubt you also realize that if you go slower on an on-ramp or off-ramp, that you feel less acceleration. Now, radius also plays a portion. Obviously, you've probably noted that if the radius of the on-ramp or off-ramp is small, you feel a greater pull, and if that radius is larger, that acceleration that you feel is smaller. So what happens is the actual equation for uniform circular motion, centripetal acceleration, is proportional to the magnitude of your velocity. So that is your speed squared divided by the radius of the circular path you are traveling. Again, that is the magnitude of your velocity squared divided by the radius of the circular path you are traveling. So let's look at a problem. Here in question 1, we have a rock tied to a string that's traveling at a constant speed of 4 meters per second in a circle of radius 1.5 meters. Now, what we're going to try and do is we're going to calculate the magnitude of the centripetal acceleration of the rock. And we also need to figure out what is the direction of that acceleration. So first things first, the centripetal acceleration is going to equal v squared over r. Now our velocity is 4 meters per second, so we're going to square that. Our radius is 1.5 meters. So what we're going to have is 16 divided by 1.5. Now 16 divided by 1.5, that's just going to be right over 10. So that's going to be 10.67. And our units are going to be meters per second squared. And this is going to be radially inward, or towards the center. So either way is equivalent. So let's look at another question. We have a rock tied to the end of a string and moves in a circle at a constant speed of 2.5 meters per second. It experiences an acceleration of 4 meters per second squared. And we want to find the radius of the circle of that motion. First things we're going to do is we're going to start back with that same centripetal acceleration. That centripetal acceleration is equal to v squared over r. This time we're solving for r, so what we get is that the radius is going to equal v squared divided by that centripetal acceleration. Our velocity is 2.5 meters per second. We're going to square that, and we're going to divide it by that centripetal acceleration, which is 4 meters per second squared. So 2.5 squared divided by 4, that's going to give us a radius that's just over 1.56 meters. Now we do have to realize when we're looking at circular motion that really what's causing the circular motion is a combination of forces, a net force. Because we use this so frequently, we often give a name to this shorthand of net forces that we use constantly, and that is centripetal force. Now, if you're drawing a free body diagram, centripetal force is never listed because it is a net force. It is not a force independent of itself, it is a net force. So when we're talking about centripetal force, we're talking about a net force. So that net force must be directed towards the center of the circle. An example of where we could use that information would be, for example, in this question. We have a 1.3 meter long fishing line. It's rated as a 10-pound test line. It can withstand a force of 10 pounds, and it's attached to a rock that has a mass of 5.5 kilograms. Now, we're going to say we're going to rotate this rock in a vertical circle, and we want to find the maximum speed we can rotate this rock at without breaking the line. So, first things first, if you look at the circular path, where the tension of the string is going to be the greatest is going to be right here at the bottom. At the bottom, you've got the force tension pulling upward. That's what's going to create that changing force. And we've got the force due to gravity going downward. So at this point, that tension is going to be the greatest. So if we look at the net force, and we recognize that that's equal to mass times acceleration, it's centripetal since we're moving in a circle, our net force is going to be force tension minus force due to gravity. That's going to equal mass times v squared divided by r. Now, force tension, if we want it just before the string breaks, that's going to be 10 pounds, which is 44.48 newtons. Force due to gravity is going to be the mass of the rock, which is 0.5, times gravity, which is 9.8. That's going to equal the mass of the rock, which is 0.5, times velocity squared, over the radius, which is 1.3 meters. So first let's simplify the left side of our equation. So we have 44.48 minus 1/2 times 9.8, that's 4.9. So that's going to give us 39.58, and that's going to equal the 0.5 times v squared over 1.3. So what I'm going to do is I'm going to multiply by 1.3 and divide by 0.5. So 1.3 times 39.58 divided by 0.5 is going to be my v squared. So I multiply that by 1.3, divide that by 0.5, I get 102.9. That's going to equal my v squared. So to find my velocity, I'm going to take the square root of that answer and get that my velocity is just over 10 meters per second. It's 10.14 meters per second. So that tells me exactly how fast I can spin that rock before the line breaks and the rock goes flying off to hit who knows what. Now there are two practical applications we see with centripetal motion when we're driving a car. One of them is when we are driving on a flat curve. If we have a flat curve, that means that friction alone must be enough to produce that centripetal acceleration. Now, oftentimes when we're looking at on-ramps and off-ramps, we have a banked curve. That means not only do we have to rely on friction, we have to rely on a component of the normal force in order to create the force that holds us on the curve. If we go too fast or we go too slow, we would go up or down that banked slope, which could be very dangerous. So we have to be absolutely careful about that. Now if we go back to a rock on a string, or a ball on a string, and we start moving it in a horizontal circle. In order to move it in a horizontal circle, the tension in the string must be at some angle, with the vertical component countering the weight of the object and the horizontal component creating that centripetal acceleration that we need. So what happens is that as we spin it at higher and higher speeds, that string will come closer and closer to a horizontal plane, so that angle is going to get smaller, and that's because we need a larger component of the horizontal tension in order to provide that net force needed to keep the object moving in a circular path. Now, other places we may see this kind of motion: Ferris wheels, roller coasters, cars going up and down hills. If we look at uniform circular motion on a Ferris wheel, at the bottom of the Ferris wheel, you feel heavier than usual. That's because your normal force has to be large enough to produce that circular motion that gets you moving along that circular path, that centripetal acceleration. So what happens when you get to the top is that if the ride is tuned just right, you won't be in contact with your seat. There will be no normal force. So you will feel significantly lighter at that point. Now, in reality, not all rides are tuned just so, because we all have different masses. So what happens is there's usually a small normal force, but it is really the weight of the person that is providing that centripetal acceleration towards the center of the circle. So, work on Chapter 5 questions. Bring me questions next class period. Make sure you've worked the examples for sections 5.1 and 5.2.